Step 5.3, model-based methods. We're looking at finite mixtures of binary distributions now when using the interactivity dataset from package MSA, which we loaded here. So we're loading here to to cluster that data now using mixture models. We are setting a random seed because we're using the EM algorithm to fit the model, and function step flexmix from package flexmix implements the EM algorithm for different kinds of mixture models. So what we specify here is what kind of data we want to use, and we're using a formula interface to do so. So we have as dependent variable our segmentation base in model-based clustering, where we specify here the matrix of the binary variables, and we're not in a regression setting, so we don't have explanatory variables to the right of the tilde, which means here we only have an intercept. We're fitting finite mixtures for a different number of components or clusters. Here we specified for 2 to 8, and each number of clusters will be run with 10 different random initializations to increase the chance of finding the global optimum, and then only the best among these 10 random initializations will be returned. And in the argument model, that's the important argument where we specify what kind of mixture model do we want to fit, what's the model we put into the components, and here we want to have multivariate binary data where we assume that the agreement for one variable is independent of agreement for all the other variables. So we can specify it as a product of Bernoulli distributions, and that's done using here this model FLXMC MV binary, which says it's model-based clustering. That's the C, and we have multivariate binary distribution, and we don't want to see progress information of the fitting on the screen. That's where both equals false. Running function step flexmix takes some time, but the result can be plotted using plot to give us an overview on how the different fitted model compare with respect to the information criteria. So we get the results for ICL, BIC and ASC, and the solid points here indicate where the minimum occurred. So for ICL the minimum occurred at 4. For BIC at 6, and for ASC the smallest we observed between 2 and 8 was 8, so we would need to continue fitting more components to decide on a suitable number with the ASC criterion. We see BIC selects less than the ASC, which is what we would expect. And if we look at the shape of the BIC criterion, we see a rather steep decline until 5 components, and then it flattens off. This is something one also often observes with the BIC criterion because it tries to measure goodness of fit and not necessarily the clustering property. So if we look at how long did we see a good decrease, or the decrease was rather large, and then it flattens off, we would select 5 number of components. So subsequently now we'll look at the 5 component solution. We'll select the 5 component solution with function getModel. Use the subflex class object returned, and then we specify what model are we interested in. We can here either specify the criterion. We tell getModel to select the one with the best ASC, BIC or ICL criterion, or we give the number of components we're interested in, and here we say we want to have the 5 component solution. This now returns an object of class flexmix. We see how it was generated. That's the cluster sizes if we assign respondents according to their a posteriori probabilities to components, and this is the information on the EM algorithm if it converged or not. Using that clustering, we can generate a profile plot for the centroids we obtain using that clustering, and we can use function prop bar chart from package flex class to do so, where we put in our data set, and then we have a grouping variable. We have here the grouping variable is the clusters we are extracting from our fitted model, the hard clustering, and then we are looking at what's the proportion of agreement in each of these groups for the winter activities. Note that here the winter activities is already the segmentation base, so it's not correct to run tests on it, and that's why we set alpha equals 1, and strip prefix just indicates what should be the labels for the strips. So let's zoom in. That would be now a profile plot for the result using the mixture model, where we get the bars again indicate overall agreement with each of the winter activities within that segment, and red dot is the overall agreement with each of them over the whole data set. And we can compare these two again to see where does this segment differ from other segments. We also see the segment sizes, how many observations are contained in each of the segments. And we could now try to look at this to interpret results, and we can also compare this solution to the k-mean solution.